With the fast development of smart mobile phones, now people more prefer to shoot their exciting moments on their phones. Oh wait, the moment is fleeting, only leaving us some blurred images. This phenomenon is called motion blur, which is mainly caused by a long exposure time to record fast-moving objects. A longer exposure time generates a more blurred images. Three major ways are used to elevate this phenomenon. A professional training is always welcome to control the exposure time, while this is impractical for most users. We can also reduce exposure time, while this brings more noise and low-quality photos. In practice, people focus more on the deblurring techniques, especially deblurring faces. Two major methods are mainly used. One is blind deconvolution method, which treats the motion blur as a slowly varying kernel and is suffered for processing out of one movement. The other is deep learning based method, which requires expensive computation that is constrained by most mobile phones. Therefore, it's challenging to deblur high-resolution photos on mobile phones. To solve this problem, the paper Face Deblurring uses dual camera fusion on mobile phones. Try to solve it based on two components. First, design a dual camera solution in which the input is captured by wide camera and the reference used for deblurring is captured by ultra wide camera to generate high quality outputs. Second, deploy the designed solution on mobile phones. The pipeline of the solution mainly contains 5 steps: pre-processing, image alignment, image fusion, blending, and post-processing. In the pre-processing step, the authors use some existing works to chop the face images for deblur, including mixing the bursts, obtaining the face marks, and matching colors between the input and references. Next, to align the optical center of both cameras, they also use the existing PWC network to estimate the occlusion based on the downsample source and references. They also use the forward and backward flows obtained by the network to generate the occlusion marks. The network is optimized for mobile phones so that only 13 microsecond delay and 34 megabytes memory is required in practice. When deblurring, they also design a U-Net variant network for deblurring, which take inputs from the source, references, face, and occlusion marks. Similar like before, this network is also optimized, only requiring 300 megabytes memory on mobile phones. The deblurred image is blended back to the source based on the alpha blending method and is further processed via various methods to generate the final sRGB image. A poly-blur-based method is also used to remove mute blur and enhance sharpness. Fallback mechanism is used to automatically fall back to the source image to capture a low-quality references. To deploy the solution on mobile phones, they first optimize the deep learning models to meet the hardware and runtime requirements. Then, they adaptively turn on the ultra-wide camera to avoid unnecessary power consumption. The ISP pipeline is also optimized to support the fusion deblurring with photo capture at last. The overall results show that this algorithm can successfully deblur images on mobile phones to generate a clear and sharp face. They also compare the results with previous ones, and the algorithm outperforms others in most scenarios. They test the algorithm runtime, and they find out only 27 microseconds is required to deblur a small image and about half second to deblur an image on Google Pixel 6. Furthermore, they validate the contributions of some key design within the solution to show their necessity. They also compare the results with some commercial products to illustrate their efficiency. Finally, they simply discuss the limitation of this algorithm, including effect caused by the reference quality and face size. In conclusion, this paper proposed a dual camera solution to deblur runtime captured photos on mobile phones, and the evaluation results show that the algorithm outperformed all existing works.